excited to tell you a little bit about the work that I have done using museum collections to try and predict something about the future. So I'm sorry to tell you, you've not made it to the physics portion. We're not actually talking about time travel yet. Basically what you're looking at here, the temperature anomaly from a 35-year period, most of which I remember as I was alive for those 35 years, but basically comparing temperature anomalies to a base period. Yep. So the main takeaway from this is that we're a full degree warmer in August of 2016 compared to the preceding 35 years. And while I think this is a super cool visualization, there's no spatial information. So what you're looking at here is basically the same thing, but over spatial extent. And the take home here is that high elevation sites and high latitude sites are warming more rapidly. Now this begs the question for animals that are at these sites, are they able to keep up? And there's been a lot of debate about keeping pace. I'm happy to report that there is some evidence that animals are able to keep pace with climate warming. My first example here is this little snowshoe hare. So it molts both from brown to white and then again from white to brown. And as you can see, they're quite visible if they're mismatched with their environment. Like that looks like a really tasty hare. That looks like a really cryptic hare. So these molt rates are very important. So the molt from white to brown is now faster. They've been able to speed up that molt so that they're able to match their environment more quickly with earlier snow melt. Another example are these cute little marmots. They've been in the news lately because of their social structure, but basically they hibernate over winter, and they've been able to keep pace by waking up sooner when temperatures are more suitable. Now this does mean that they have a longer period with which to eat, so we're getting fatter marmots, but they're at least awake, taking full advantage of the growing season. And my last example is from another Scandinavian country where we have these silver-washed fritillaries that are actually shifting their geographic extent in response to climate change. So for my study, what I did was I identified an alpine butterfly that should theoretically be experiencing these increased rates of warming. I can't quite compete with Bodil's field pictures, but this is where they hang out in these alpine meadows, or from their perspective, from an alpine clover. That's their little host plant. They're laid on these host plants as eggs in the summer, and they hatch out as these little first instar larvae. Then they eat and eat and eat like the hungry caterpillar, and then when they hit this third instar, they basically go into diapause or dormancy, where they will be covered in snow for the winter. So they overwinter as third instar larvae. And once the snow melts, then they're able to resume development and turn into this beautiful butterfly. Now, when that happens is highly variable. So you can see in 2011, if you're looking down valley at these maroon bells, 2011 was very snowy. Snow melt was very late. The next year, it was a small snowpack with early snow melt. So there's a lot of interannual variability. So alpine environments are actually pretty similar to high elevation or high latitude environments like Denmark. So what determines your body temperature when you go outside?
Wind.
Wind, yes, absolutely, wind. I cannot tell you how many times I'm like, it's such a nice day, but it's super windy. Anything else? Air temperature, fantastic. Anything else? The jacket you're wearing, yes, exactly. I like to say the presence, or more frequently here, the absence of sun, the ambient temperature, and of course wind. So windy. And Bodo mentioned a jacket. So our butterflies have actually adapted to their local environment they don't quite have the equivalent of a butterfly jacket, but they do have these really hairy thoraxes. So they have these modified CD that basically create this insular layer that functions kind of like a cute little butterfly jacket. The other thing they have are these dark melanic scales. Can you think of any reason why you would want dark scales? Yeah. It basically acts like a giant solar panel to absorb the solar radiation and increase heat. So you can see, kind of taken together, these climatic variables interact with these morphological traits. to determine their body temperature. Now, butterflies like us do have some faculty in terms of how they're able to regulate their body temperature. So if they're quite cold, what they will do is orient those dark scales towards the sun. Unlike some butterflies, these are closed-wing baskers. So they do actually act like a little solar panel. And if they get too hot, they can avoid the sun, they can orient away or drop down into the vegetation. But not unlike Goldilocks, what they're aiming for is that sweet, sweet middle temperature where they can fly. And activity is really important because it allows you to do super cool things like eat, reproduce, and avoid being eaten by giant spiders. Female Coleus butterflies will only lay 1 egg per plant, so their fitness is directly correlated to how quickly they're able to move from plant to plant, and male fitness is obviously determined by how quickly they're able to locate a female in a field that looks something like that. So despite the ability to regulate body temperature through behavior, it would stand to reason that being the right type for your environment should be pretty strongly selected for. Now, climate is changing, as we saw in the beginning, specifically at these sites. So we have 2 representative weather stations here, one from a slightly lower elevation and one from a slightly higher elevation. But this is still the whole span of the orange sulfur butterfly here. So the dark line is the slightly lower elevation, and the dashed line is the slightly higher one. What you're looking at the top is this variability and increase in mean annual temperature. And down here, it's the standard deviation of temperature, so how variable they are within a year. So if it's getting warmer, what do you think will happen to these butterfly traits in this nice little story that I'm telling you? Do you need a big, thick coat when it gets warm outside? No, that's my favorite part of the spring, stitching my coat. Do you want to be a big solar panel? No. So what we did was we decided, rather than trying to go forward in time or convince our physicist neighbors to build us a time machine, I would utilize the relatively untapped resource of natural history museums. Now, I know many parents are familiar with natural history museums because it's a nice place to go when it's raining and your small children need to get out of the house. But they also house tens of thousands of specimens that aren't typically on display. So what we were able to do was identify a number of institutions that had large collections of this Rocky Mountain species and go in and sample those collections. What we were able to do is get a pretty decent spatial distribution of samples and pretty decent coverage over time utilizing this. So I visited these various museums. You can get a good sense of what they look like when you open up these boxes. And then I would tip them over and photograph their ventral hindwing, and then also measure their thoracic cedal length. And then was able to take those photographs back and digitize them and use the power of MATLAB to determine what I would call a grayscale, or a proxy for melanization. And what we ended up with was just shy of 380 males from 1954 to 2012. Now, I think we have some bioinformaticians in the crowd, so they're probably already keenly aware of the fact that we need, if we're going to correlate things back to temperatures, we need some decent representation of climatic data. So that's sometimes a little bit of a challenge because we need something that can go back in time, 60 years. So we identified the climax weather station, so it's at an appropriate elevation, pretty centralized location, and had good temporal resolution. So we were able to pretty much come up with a list of predictor variables of things that we thought might be affecting these traits. So we looked at year of collection, selection on the parental generation, which is basically just what we calculated as temperature in the previous flight season. Then the date of collection in the year, so if they were caught in June or July or August. And then we back calculated a pupal temperature, thinking that developmental temperature might have some sort of effect on adult traits. We had some challenges with our data. It's possible that our sites or our collections were non-independent, so we dealt with some spatial autocorrelation. And the other thing is, because I don't have a time machine, I couldn't determine how many samples people took from a particular site in a given year. So to get around that, we did some fancy bootstrap so that we had 15 individuals per year, and repeated that 50 times. So now, as your eyes glaze over, these are my statistical models. Basically, I want you to bear in mind that I'm trying to look for a genetic effect and some sort of effect of environmental temperature. And what you're looking at here, I know it's a lot, but these are regression plots. So these are each of our individual predictor variables, and then it's the partial residuals for that one. So we'll just focus on the things that are interesting and important. So as the season progresses, so you get later and later in the season, we notice that individuals tended to be lighter. And contrary to our expectation, as we came closer and closer in time, individuals tended to be darker, like quite a bit darker, like 20% darker. So like, well, maybe they're losing heat, maybe something's going on with their thoracic CD. So we used the exact same model and used thoracic CD as our response variable. What we found here is that in years following warm years, so if the parental generation had a really warm summer, the next generation had really long thoracic cedal length. And they also have evidence of increasing thoracic cedal length over time. So what happened? This is not at all what we predicted. So maybe we missed something. So we decided maybe we should look for a shift in phenology, since we know that there's a great deal of interannual variation, and that variability could determine diapause termination and developmental rates, and when they're going to exit that third instar and start progressing into the fourth instar. So warmer springs could trigger an earlier snow melt, but that would also mean maybe a cooler developmental time and a cooler flight season. So when we look at that, we actually saw that collection date was increasing over time, but that also was confounded with elevation. So as you increase in elevation, the collection date advances, which makes sense since mountain peaks tend to be slightly cooler than valleys. But what was really interesting is that we see this advancement in collection date at low elevation sites. So that means that there's something different happening at lower elevations versus at higher elevations, which makes sense if you think snow might be melting sooner at lower elevation sites. So what did we actually learn? So warmer developmental temperatures and late season collections tends to decrease wing melanism. So that's an indication that there's some sort of plastic effect going on here. We see some evidence of phenological shifts. So we kind of are increasing the growing season at lower elevation sites, which might actually confer some sort of advantage to being slightly darker, slightly furrier. But the main take home from my perspective, and the thing that I think is really important, is that while we're using these museum collections, and I think they're a great resource, they're casting a light on the fact that evolutionary responses are complicated. And even when we think we have a clear hypothesis of how things should respond, the ecological and evolutionary responses can either be limited by environmental variability, or by plasticity, or by trait range generally. So yeah, I think it's a great example. Museums are a great resource, and responses to climate change are more complicated than you might think.
Thank you, Heidi.